Hello, AP Calculus AB students. Here we're going to discuss page 4 of the section 2.3 notes. And we're going to start off with example 8. So example 8, you're told to, give a formula for the extended function for sine 3x over x. It says continuous at x equals 0. Well, if you were to graph it, you would see that there is a hole right there. You can do that in Desmos as well. Also, if you plug the numbers close to 0, you're going to see that eventually y will get closer and closer to 3. So we know that the limit, we've done this before many times, sine 3x over x will equal 3, because generally speaking, we have sine kx over x, the limit as x approaches 0, that's just going to equal k. So we just label this like such, 1, 2, 3. But anyway, we want to write an extended function so that it is continuous at x equals 0. Because remember, to have continuity, 3 things has to happen. F of 0 must exist, which right now it does not. The limit as x approaches 0 must exist, which of course it does. We know it's 3. And f of 0 must equal the limit as x approaches 0 of f of x. So it means that we need f of 0 to equal 3. That's what this tells us. All these rules of continuity. So in order to make it work, we just do this. And actually, I should probably write the subscript ext to show that I'm extending this function to include that. So write the original. And of course, it's true for all x except 0. And then we just write 3 at x equals 0. That way, by doing this part, we can plug in that hole. So, excuse me, essentially what you're doing is you're writing it as a piecewise function, and you're extending the function by plugging in the hole. Now, what are examples of common continuous functions that we'll see in this class? Definitely polynomials. Definitely rational functions. Trig for sure. Logs for sure. Exponential functions. So there's kind of a variety. And that's because all these here any point excuse me, of discontinuity won't be in the domain. So we could see discontinuities happen for rational functions like 1 over x, or for trig like tangent x. Oh, that's not working. Or for logs like log x, or there's parts of the functions that are they're not going to be defined necessarily, but they're not part of the domain though, right? Because we exclude it. So we still consider these to be continuous functions as long as anything in this domain is fine. But sometimes we wish to make things continuous at particular points, like in this case here, even though this is continuous in its domain, but we want to make it continuous at x equals 0, because 0 was not part of the domain, so we forced it by doing a piecewise function and plugging in the hole. Let's look at the table here. So properties of continuous functions. Again, what if you have two functions? So you call them f and g. And they're continuous at x equals c. Then the following combinations are also continuous. If I add them, subtract them, that should be at times, by the way. That should be another times if you have a constant next one, or if you divide them, provided that the bottom does not equal 0 when you plug in x equals c. Likewise with continuous functions, with composite functions. A composite Oh, it looks like my stylus died. Don't know how that happened. We'll have to charge it. Okay. Likewise with composite functions, when you plug a function to something else, we have experience with this. So say, for example, if f of x, g of x, and h of x are all continuous functions, verify that this wacky thing is also continuous. What you could do is you could deconstruct this. So we know f of x is x, and g of x is 5, and the whole thing, the cube root right here, is h. So you could initially start by doing this. The cube root, I can do that better, of 7 times f, and I'll write just f sub f of x because it just kind of gets to be a little too busy, plus g itself. And because the whole thing is a set of cube root, we can write as h of 7 f squared plus g. And so each of these are continuous, right? That's continuous. 7 is continuous. F squared, using f times f, each of those are continuous. You have two identical functions being multiplied together. So altogether, this whole thing is also continuous. So I know it looks a little weird, but remember, it is a cube root after all. You can cube root whatever you want. So there's no reason why there's any breaks in this graph if you were to graph it. So that's just something to keep in mind, that if you have all the individual parts of the continuous and you're plugging one thing into the other, the combination of all of it's still continuous, just so you know. All right, that ends page 4 of this video.